The fancy name for the topic of motion is dynamics. I can see you're impressed. Newton's laws of motion, as they were originally written in Latin. Anyone do Latin? Did anyone do it back in year 8? Oh, there you go. So you know what this says there. Hey, corpus omni persevere, in statu suo quiescendi vel movendi, uniformita nisi quatentus. I'm sure Mr. Salter could say this so much better than me. Okay. All right, for those who can't read Latin. So basically the first idea is, it's a very simple idea. Everybody continues in a state of rest or in uniform motion in a right line unless it is compelled to change by a state of forces impressed upon us. In other words, we're going to keep moving unless some force acts on us to stop us. Or we're going to stay stationary unless some force comes and pushes us and gets us off moving. Okay. That's all it really says. The second one's the famous one. I've been showing you motus proportionalium. In other words, the change of motion is proportional to the motive force and is made in the direction of the right line in which the force is impressed. And I know I'm impressed. So, motive force basically proportional to change in motion. Well, motive force, change in motion is acceleration. So force is proportional to acceleration. Now force therefore is equal to some constant times acceleration, and that constant is mass. And we get that very famous equation, which I'm sure we've all seen before. Force equals mass times acceleration. So that's the second law. The third law, actione contrarium. No? Okay. To every action, there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed in contrary parts. Oftenly quoted as to every action there's an equal and opposite reaction. You've probably heard that before. But what it's basically saying is this. So look, I'm standing here right now. We know that gravity is acting on me. Right? And yet, I'm not being dragged through the ground. Because there is an opposing force balancing it out, and I'm not, therefore, going down. Thanks to the ground. Thank you, ground. Ground is putting a force on me as well, and I get to stand up. So there is always a balance in the forces. So the sum of all your forces is equal to 0. And that's the idea. That's the key idea we're going to need to use as we go through this topic. So, all right. Force is important. Force is mass times acceleration. Mass is just a constant. Acceleration becomes the interesting bit. Now we have seen already that we can write it with respect to time. So second derivative of displacement with respect to time. First derivative of velocity with respect to time. So that's when we've got acceleration as a function of time. Now we've also seen d dx of a half v squared. And that was useful when acceleration is a function of displacement. But you'll remember sometimes I use this idea, v to v dx, was also useful for function of x, but comes in very useful if acceleration is now a function of velocity. That I can rearrange it and get to v and play around with it. So these are the three, well 4 if you count the v to t as being different to d2x to t2, but the 3 ways we can think of acceleration depending on the problem and how we want to end up with a solution in terms of what variables. I'm now going to show you a really, really old question. Back in 1981, you'll find in a lot of questionnaires to me they didn't put a lot of numbers in it and there were a lot of just pro-numerals. So let's have a look at it. We're going to assume the Earth is a sphere of radius capital R, and then at a point little r, which is bigger than capital R, otherwise we'd be inside the Earth. From the centre of the Earth, the acceleration due to gravity is not g, but it's proportional to 1 over r squared and is directed towards the Earth's centre. A body is projected vertically upwards from the surface of the Earth with an initial speed of capital V. we're going to prove that it will escape the Earth's atmosphere if and only if that velocity is greater than or equal to the square root of 2gr, where g is the magnitude of acceleration due to gravity at the Earth's surface. Okay. The blue circle there is representing the Earth, in case you haven't worked it out. The red line, I'm going to define that. There's the straight line. It's basically straight line motion. So that's the straight line that I'm moving along. Now they've given me some, oh, there's good old Bob. We're going to get to know Bob over the next week or so. So Bob is the particle that's moving. We like to call him Bob. Well, I like to call him Bob anyway. At the Earth's surface, what do I know? R, remember, is our pronumeral. They thought they'd cleverly call it R, why they couldn't call it X. So we could go, oh yeah, we're used to X. No, we're going to use R. So R is capital R at the Earth's surface. Velocity is capital V. Acceleration is negative g, because they said it was directed towards the centre. The other thing I know is, well, when it stops, velocity will be equal to 0. That's really all I know about this problem. So there's Bob. So what we do in extension 2 is we start with the forces and we say, good old Bob, what forces are acting on this particle? Now, this is not a force. This is the resultant force. This is, once we add all our forces up together, it will give us an overall result. And if it's like me standing on the ground here at the moment and nothing happening, that result would be 0. But if I was jumping, apart from you probably laughing at me, it would have some value to it. So in this problem, we don't know what the resultant force is, but we define the resultant force to be positive. So I always point it in the direction of positive. Now, if I had wanted to with this problem, I could have pointed it down and decided that positive would have been the down direction. We're not fixed by our actual number plane where negative is down, positive is up. We can define it however we like, but it does make sense to define up being positive, so that's how I've done it. I'm travelling up, so I like to define the direction I'm travelling in to be positive. So it's not actually a force. I chose a different colour for the actual forces. So the only force acting on this is the force due to gravity, which they said was proportional to 1 on r squared. Well, they said the acceleration was proportional. But force is equal to mass times acceleration. So I've got m times 1 on r squared, but it was proportional to it, so it's equal to some constant times that again. So I've used the Greek letter mu, because I always find it amusing when you put m next to mu, because it looks like mu anyway, so you go mu, like a cow. Okay, anyway, but I could have used k, it doesn't really matter. So all right, all of my forces, mr double dot, are equal to, well, there's only one force. It's m mu on r squared. It's in the negative direction, so negative. So all of my forces should add up to be minus m mu on r squared. That is the starting point of the question. And of course, the nice thing here is, mass will cancel on both sides for this one. So I get my acceleration, and it's in terms of displacement. It's in terms of r squared. I'm going to actually work out what mu is. They gave me some information which allows me to work out mu, because I know when r is capital R, the acceleration was negative g. So let's sub that in. Mu, is equal to g capital R squared. So my acceleration equation now is minus g capital R squared on little r squared. Now I prefer that because that's in terms of all the variables they've defined rather than mu, which I just threw in there because it was funny. So okay, it's in terms of displacement. Remember, little r is representing displacement. So it probably means I'm going to use either v to v dx or d dx of a half v squared, one of those two. So v to v d, well, it's not x, it's r for this one, but v to v dr is equal to minus gr squared on r squared. I'm going to separate the variables, Okay, now let's think about the problem. The problem said when displacement was capital R, the velocity was capital V. So I've matched up the limits. I'm going to come up with an equation for velocity in terms of R, which is our displacement. Integrate both sides. You'll notice instead of going a half V squared, I've multiplied the right-hand side by 2. But integrating 1 on R squared, I get minus 1 on R, but the minus then cancels. Okay, so V squared, actually, you hate it when they use the same pronumerals. V squared minus V squared, because big V. V squared is equal to 2GR squared on R minus 2GR squared on R. So the big R's as opposed to little. It would have been so much easier if they picked X or something like that. But anyway, there we go. All right. Well, that tidies up. I'll move the capital V squared onto the other side. The 2GR squared and the R cancels. I have an expression for the velocity. Now we're trying to find that escape velocity where we never come back. Well, if we never ever come back, then my displacement is going to approach infinity. I'm never going to stop. So she's going to keep going, keep going. Might take a long time, but that's where we're going. So I want to find what is the limit of V squared as little r approaches infinity. Well, have a look at our equation there. And V squared, that's big V squared, minus 2G big R, they're all constants. The only place where there's a little r is on the bottom of a fraction. Well, we know, I mean, if we look at our hyperbola, there's the classic example, y equals 1 on x, as x approaches infinity, that curve's going towards 0. So the 2G capital R squared on little r, we know that bit will go towards 0. So I'm just left with V squared, capital V squared minus 2GR. That's the limit of V squared. But okay, this is where it gets a bit strange, because what we're now going to think is, if it did happen to reach, because what we're saying is, if it did happen to reach infinity, this would be V squared minus 2GR. But that's when it's going to stop. When it actually reaches infinity, because it never stops until it gets to infinity. So what we're really saying is, hey, that's equal to 0. But I suppose a better way of thinking about it, because that's probably confusing, thinking, hang on, it doesn't get to stop until it reaches infinity. Let's just go back to the idea of, look, I know V squared is always going to be greater than or equal to 0. So capital V squared minus 2GR must be greater than or equal to 0. Well, let's just solve that then, and we can work out that initial velocity. V squared minus 2GR is greater than or equal to 0. V squared must be greater than or equal to 2GR. Now, I don't have to worry about plus or minus, because we know it's never going to have a negative velocity, because remember, it's going up, but it's never coming back. So it's always going to have a positive velocity. That'll be the square root of 2GR. So in order for the particle to never stop, that velocity has to be greater than or equal to the square root of 2GR. Let us assume now that we are going to send it off with that escape velocity of root 2GR. I mean, anything bigger it will as well, but that'll be the smallest velocity it could be. We're going to work out the time it takes to rise to a height of capital R above the Earth's surface. So the Earth's surface was at capital R. We want to know how long it takes to get to 2R. So another R above the Earth's surface. They've given us the answer just to help us out. So at least we can see if we're on the right track, which was nice of them. So okay, there's our formula. V squared equals that. But we're now saying V is the square root of 2GR. That's really nice, because if V is the square root of 2GR, these two bits at the end cancel, and I've just got a little equation like that. So V squared is 2G capital R squared on R. I have velocity in terms of displacement, or velocity squared in terms of displacement. So let's make it velocity. Again, I've made it the positive square root because it's not coming back. So I know it can't be the negative square root. So square root of 2GR. Now I'll make velocity dx to, well, in this case dr to t, but dx to t. And we can now integrate. Well, we're going to have to turn that upside down. So I've got the TDR, square root of R on 2G R squared. But they're all just constants. It's basically the square root of R that I'm going to integrate here. So let's separate the variables. So I've pulled all that constant out, because as I say, all I'm really integrating is the square root of R. Now, when time was 0, we're at the Earth's surface, capital R. We want to know what the time is when we get to 2R. Integrate. Left-hand side just becomes T. That'll be the time that we're trying to work out. Add 1 to the power over the power, 2/3 R, 3 on 2. I just got to substitute in R and 2R. So I know that R to the 3 on 2 is the same as R root R. So substitute in 2R, I get 2R root 2R. Substitute in little r, I get R root R. Now, what else have I done? Oh, I pulled out the 2/3. Root 2 cancelled into the 2 to give me root 2 on top. And then I've got 3 on the bottom. Now, 2R root 2R minus R root R. All right, I've pulled out a common factor of R root R, which leaves me with 2 root 2 minus 1. Now, it's not on this page, but if you have a look at what we're trying to prove, you can sort of see why I did that. I'm trying to head to that answer. So I've got root 2 on 3R root G. But hang on. R here would cancel with that R, so I can get rid of that. So what have I done? Yep, I've got rid of the R, so I now have got root R. I've put the root 2 into the parentheses. So 2 root 2 times root 2 is 4. 1 times root 2 is root 2. And I think we're close. Is that what we needed, or? Oh, okay, so then we wrote it as 1/3, 4 minus root 2, the root of R on G. And that was what they were looking for. I'm only giving you 3 questions to start off with to play with. All right? Because I actually think that looks complicated, what I just did. Once we actually look at the next bit, it'll make it a lot clearer, I think. So it's just 3 to play with. Have a go at it. Don't panic. Because as I say, I'm pretty confident it'll become a lot clearer when we move into the next bit. It's just get a feel for the idea.